with the microphone, so it's good. Thank you very much for the invitation, Thomas and Vicky, and thank you for this rather long introduction. So hopefully nobody just fell asleep during that introduction, and especially since I'm actually staying with a very boring talk, hopefully not that much, between you and the lunch. So bear with me. When Thomas started the meeting with just showing this beautiful video of 1994, it just reminded me that actually my very first fMRI experiment was also in 1994, probably only a few months after, as I started my PhD then in Zurich on that field. So this current meeting brings me back to my roots in this field, and I just wanted to show these. I just added those to my publications as well. So this, I set up the whole system in Zurich at the time. There was no NordicNeuroLab, so we need to do everything. So you can see that we put, I'm going to put it here. We put the, you can see it. You have the scanner and etc. And they set up a very large mirror and a projector, which was like with a three, it was like an old beamer with three colors independently and stuff. And here you could see that for the fMRI bit, we also had a video recorder, because at the time you needed to create a video on a very special hardware and then play it to be able to have something that was actually moving. So just ages. And that was how it looked. We could look behind, and you had this nice, semi-transparent screen projected from behind. Anyway, that was then. What I'm going to talk to you today is about quality assurance in fMRI. I think it was mentioned a couple of times before, and it's really about making sure that your scanner, just before you start with the advanced paradigm and data, etc., making sure that your scanner actually works well enough for you to detect both fMRI and also actually DTI or ASL or any of these advanced methods that you want to use, to detect them properly. So the outline of the talk is just going to go first with a small introduction about why you need it, then look at what has been set up. And in this particular presentation, I'm just going to use something that has been set up now 20 years ago. And the reason we're using that is because there are actually some historical data we can compare it to, and also because it gives you a baseline about what you can do to test your scanner. Then we'll go about the metrics that are being used for quality assurance in fMRI, and some of the results that were used in an early trial that was published again 18, 17 years ago. Then I'll just go to our solution, the company I'm representing. I'm only a honorary professor in this case, which is very honorific, and I'm really a company man, just dressed like one. And I'll just show you a quick demonstration. So, background. The bold signal that everyone is actually interested in this room is very small. At a clinical field strength, we're not talking about 7 Tesla here, especially 1.5, but even 3T, we're talking about a few percentage of signal changes. So the scanner stability, and then by that I mean really the gradient and the RF, the two main components that will actually give you an image, needs to actually be very, very robust, because if it's not very stable, you'll not be able to detect some small changes, because as it was hinted previously, you see or you don't see an activation. Well, the activation is always there. It just depends on the threshold you're using. So it's just, you need to make sure that the statistical threshold means something, and therefore that the amount of analysis that you're doing is based on data that are meaningful. So why is this critical? Well, we've done 2 different applications, but so far the main application that I've heard here was about clinical practice, right? So in clinical practice, a poor MRI signal stability can lead to, quote unquote, and I'm just going to do that a lot, reduced activated areas. Reduced activated areas means, yeah, we don't know, there is something, and etc. And then the plenary speakers really highlighted the difference between cognitive neuroscience, where you just want to make sure that what you're seeing is actually present, and clinical practice, where actually you want the other way around. You want to make sure that there is, if you detect something, there is really something. And this is particularly important in two cases. For higher cognitive tests, if you go beyond just hand mapping or visual stimulation, but also, and something that is a lot of the case, and I could give an entire 1 hour lecture on that, but you don't want me to, which is about how vasculature can actually affect the bold signal, right? If you have a lesion, whether stroke or hemodynamic-based lesion in the brain, it will affect the delivery of the blood to the tissue, and that can affect the bold signal, which, let's all remind ourselves, is secondary to the electrical activation, which is what we are talking about. So all of this means that you really need to ensure that your signal is really of high quality. Now, there's another application which we haven't seen here much, but is also getting more and more important, particularly in psychiatric disease, where actually the bold signal fMRI as well as DTI can be used as a biomarker of treatment, in a clinical trial. Now, if you have a large variability across your times or the scan times or the scanners that you're using in your trial, then that will lead to compromised results when you pull the results. And it also, this larger standard deviation will actually lead to an increase in the number of subject tested that you need in order to validate your trial. So it's actually a really important aspect, because for pharmaceutical company, the two most important parts are cost, and a higher number of subjects means a higher cost, but also it will take longer to do that. And time is the most pressing thing for any pharma company out there. So a QA protocol was developed, as I said, around 20 years ago, and this is what I'm going to just talk to you about and what has been done. So what was this QA protocol? Well, you just need a phantom and what is called these days an exam card or protocol, an MRI protocol. Now the phantom, the original phantom, here in this beautiful, at the time, groundbreaking 8-element head card. You have no idea how it changed the world at that time. For those of you who have a bit of white hair, you remember. And they just used like a centimeter, like an 17 centimeter diameter plastic ball, filled it up with doped agar gel to quote unquote match the brain tissue properties. It doesn't actually do that, but it has some problem. And it's really highlight the fact that, well, you need really to have a gel here, not water, because actually the vibration might actually induce some pressure wave in your phantom. And if you don't have a gel, this will lead to erroneous results, and actually not reproducible ones, which is what you want to have. Now for the exam card, again, we are talking back in 2005 when this was done, but nothing has really changed since. It was an EPI with relatively poor resolution, allegedly around 3 to 4 millimeter resolution, 4 millimeter slice thickness, one gap. Of course, we don't talk about simultaneous acquisition and all of these things, but the TR is typical 2 seconds and 30 millisecond echo time. You acquired 200 volumes, this is around 6.5 minutes, and what they did at the time was to discard the first two to make sure that you are actually in a steady state. These days, in most scanners, you can actually ask the scanner to acquire a couple of ones and not reconstruct them to bring the scanner in steady state. Now, let's go to the image signal analysis. So we're going to cover the fluctuation, SFNR, and static spatial noise. And this is the part where you can fall asleep if you don't like math. I'm just going to give you a few equations. Don't worry, it's not too hard. I mean, I hope so. So first of all, you acquire the data. You acquire data just like you do in fMRI. You literally acquire 200 data. but the data will look like that, where it's just like a ball. There's nothing very important. What you need to do is for each of the pixels, you take them, and what the first thing that you look at is the drift. Because, in general, your gradient will heat up when you start banging the gradients, right? They will heat up. And that will heat the local shim. And by heating the local shim, you vary slightly the resonance frequency. And that's what actually leads to this very subtle drift. Now, certain scanners have a positive drift, others have a negative drift. It's actually just a matter of how they compensate for these effects. Now, once you've actually detrended, you just took care of that drift and you just have the signal, what you can calculate is the signal to fluctuation noise ratio. So basically it's the average of the signal divided by the fluctuation over time. So it's not very complicated, but this is quite an important, because this is an important parameter and probably the primary parameter that actually highlight how stable your MRI scanner is. And with that, you can actually start looking at the static spatial noise and the SNR derived from the odd and even image subtraction. Why do you need the SNR to be derived from odd and even subtraction? Well, it's a very simple reason. These days, nowadays, the reconstruction of the images is actually also based on some nice methods that are completely hidden from you. But what they are doing is they are using the noise in the image to actually optimize the image quality. And this is before AI. Once you get into AI, it's even worse. You cannot trust the noise that you have in the background in an MR image today. So the only way to calculate this SNR is to acquire two images of the same level and then basically use the difference between the two, which is what is where the static spatial noise is actually described in this equation. Now, once you've calculated that, you can actually calculate the SNR for the even and odd, but it's just looking at the mean divided by the signal to noise. Anyway, the final most important aspect, in particular for fMRI, the first two or three aspects are very important for any MRI parameter. I mean, in particular ASL, but also diffusion. Diffusion, if you use DTI, you need your gradients to actually work properly. If they don't, you're going to have very different types of images from time to time. And then all of the black boxes that leads to this nicely derived, fiber tracks and stuff and etc. rely on the fact that your data are acquired properly. So these are really important. But for fMRI, the most important part is, and I mean it for clinical fMRI in particular, is how correlated your two voxels are. How much is your signal going to change in one voxel that and the one next to it has nothing to do with this quote-unquote activation, but it's only present, the activation is only present because they are correlated. And that is actually one of the main issues that you might have. And for that, Robert Weisskopf, who used to be an amazing guy working at the MGH Center in the 90s, he passed away very early on in the noughties, developed this analysis, which is basically the radius of decorrelation. And what we are doing is looking at the intervoxel correlation as a proportion of the region of interest size. And basically, what it is it shows that if you take a single voxel, you will have a certain signal to noise. If you double the size, if you quadruple the size of the voxels, you do 2 by 2, that signal to noise will improve. Right? You have a higher signal to noise because you have a higher signal. And then you continue and continue and continue. And if you're doing that, basically, your signal to noise will actually increase linearly on a log-log space between the size of the voxel that you're using to calculate the signal to noise over, and so basically the actual, and I've looked at here at an almost perfect RDC score, as it is called. Normally, what you would expect this complete linear curve. That means that there is no problem in the reconstruction. None of the vendors are actually hiding some smoothing in there that actually might hurt. You estimate that your resolution is very high. You had a resolution very, very high for certain of your applications, and you thought the resolution is like that, but there is an inherent reconstruction filter in your MRI, which means that your actual resolution might be 2 or 3 times worse than what you expect. So in this case, it's almost perfect. It aligns with the theory, and you have a very good signal. It's not always the same. So how do you calculate? Well, again, you calculate just the coefficient variation with the standard deviation of the mean of the region of interest, or divided so you have the standard deviation divided by the mean over the region of interest. So it's very simple. And again, this coefficient of variation needs to increase. Now, if you think about it, the radius of decorrelation should be the radius after which you're losing this independence in correlation. And the way they've actually done it in the papers is they actually divided the one that you have with a single voxel divided by the maximum. So basically, in this case, what you're telling everyone is that the best measurement, normally, something that has a very narrow radius of decorrelation would be good, right? So if you have a very big one, that means all your voxels are decorrelated. And if you're narrow, it's actually very good because very few are correlated, right? So 1 or 2 would be good, and 20 would be very bad. The way they did it is to divide it by the maximum so that you get actually a good number being high and a bad number being low. So that's just a trick that has been done. But that means that you can actually, with that, very nicely characterize your system. Now, in this original paper, they've done some longitudinal monitoring, and this is just one MRI scanner. And you can see that your SNR and your SFNR are not very good in this case. And by changing part of the hardware, all of a sudden, all of the numbers go relatively higher, but there's still a wide pattern of changes. Remember, this is an old 1.5 Tesla G scanner. I mean, old. It was not old at the time, but it's in today's standards, you will not expect such a wide variation in SNR from one way to another. But by the time they changed the RF amplifier, you can see that you get your signal fluctuation to noise ratio become much more stable. So basically, once you start really checking that the hardware is correct, you should end up with something that looks pretty good. Another thing that they managed to detect also was actually a typical good versus bad coil. Well, this is a good coil, so this is the signal intensity, and this is the bad coil. And that happened actually to us, and I'm going to show that just in a couple of minutes. That was a really scary time where, for the first time, I was showing Vicky here from NordicNeuroLab, our great software, thinking with a brand new scanner from a manufacturer that shall remain almost unknown, because I think I'm going to show to put a picture that some people might recognize. Never mind, that indicates sometimes it might be useful to do. Anyway, summary of the results over there. It's like generally at 3T, your SNR should be with this protocol around. Your SFNR should be around 200. Right? If you have much higher, your scanner manufacturer is playing a trick. And the trick is the following, right? So when they reconstruct the image, they do some smoothing on a kernel directly on the raw images before you do the Fourier transform, right? But again, because it's a Gaussian smoothing in a Fourier space, it's the same as it's also a Gaussian smoothing in the real space, but it's much more hidden in the way it's done. And you could see that with the smoothing kernel increasing, well, your SNR increase, your SFNR increase. But if you're looking at your percent fluctuation or your RDC, it becomes very low. That means that all of a sudden, all of your signal is starting to be correlated. And the region over which it's correlated is much larger. And that can be really tricky if you're using that for clinical practice, right? Because you don't know what is the exact extent of the quote-unquote activation. And so this is basically what I thought from all that experiment, one of the most important reasons why you should do QA is actually just to check what the scanner manufacturer is doing. So before I'm just continuing and just getting into our solution, just one quick note. Without you knowing, the manufacturers perform upgrades on your scanners, right? Software upgrade on the scanners. And this one I'm not going to name it, but there has been instances where manufacturer might just come up with a brand new AI, with a brand new AI reconstruction process and stuff. But what they did when they did that, very trickily, they changed they changed the smoothing on the regular images, not the one reconstructed by AI. So all of a sudden, your resolution on your regular images kind of look a bit worse, but they look so much better with AI. The only thing they did was actually to make sure that you could see that very nicely, is they modified the basic default smoothing on the case space with or without AI. And that's not appearing in any manual. That's not appearing in anywhere. So even longitudinally doing everything the same, always the same, you might all of a sudden realize that, hey, hang on a minute, there's something that happened here, but you don't know why and what happened. So just a little hint that it's not always just a dramatic effect of, hey, a coil doesn't work, or we had another customer who had his gradient coil moving by 10 centimeter. That is pretty hardcore. You can detect it with this, and you can actually demonstrate that to the manufacturer, but it could be a bit of a problem. Anyway, implication for multi-center trial. QA Essential is really essential to control the variance. They said that they would recommend to use a weekly phantom scan to detect drift, hardware fault, so that you can use all of the data at the end of your trial. So what do you do in the existing solution? Well, you set up your own protocol, generally, that's what's happening. You export your DIACOM data. You need to download some tool to transform your data into something that you can use. Download some additional pieces of code that you can find. There used to be a big MATLAB package for doing all of this that you could download from somewhere. I don't think it's available now. There's a Python version. But basically, then you need to prepare a database, you need to copy the results. But basically, there's no standard procedure existing right now. So we came up with our own solution. And that's where I'm turning more into a salesman. So anyway, just to explain to you, I think you have it over there, our VERIFLUX Phantom. It's just similar to the original one, except that we don't like agar. We're using our own PLL-based gel. We dope it directly for MR properties independently. It has a mechanical stability. It's viscoelastic, so it's actually it cannot tear like the old gel was working. And more importantly, we can reliably make it without bubble. Anybody who has tried to make a big ball of agar without bubble, it's a nightmare. So we have consistent phantom across, so the results can be compared across the results. So we have this streamlined MRI quality assurance with an automated algorithm. Everything is all. So you can actually compare the accuracy across scanner. And I'm passing the cost effectiveness and all this, blah. Anyway, just one of the very, very first case we got at the Sheffield Teaching Hospital. They got their brand new scanner. They were still, I don't think it was actually accepted yet. They were still in acceptance testing or whatever. Vicky was there from NordicNeuroLab. There were several people there. And we wanted to show our great big things. And they used a head coil. And, you know, we had done that on previous cases. We knew what we were supposed to see. And the head coil showed an SNR and an SFNR around 40, SNR around 30. Like, I was very, very confused because I thought maybe our software is not working. There's something wrong and something. But eventually what happened was actually that the RF coil that had been accepted by the team based on the clinical standard that the manufacturer themselves provides. Of course, they have a strong bias about accepting anything that is possible. Right? Let's be very clear. Was actually faulty. They changed it and we finally got what they're supposed to be getting. So, yeah, absence of evidence is not evidence of absence. That's the biggest issue in clinical fMRI. So make sure that your hardware works, because if you don't see an activation, it doesn't mean it's not there. It means maybe that your scanner cannot detect it. That's the final explanation about standardization, ease of use, and precision. And I'm going to just make a quick demonstration. Yeah. Here. So this is the tool, and it will take me just not too much. So here. We have, so you just log in, as I said, just you enter your thing, and I'm just going to use this one, which is this one. And if you need to upload a new a new case, you just upload it, choose your file. This is the file that I have prepared. And you can see it's going to upload very fast because it's, I think, here you could see it's uploading from my computer, but it's uploading into the network, so it's good. It was uploaded. You will see there's an additional point because it was acquired on the same day here, and it's not going to take very long. In the meantime, you can switch here between the signal to noise, the SFNR, or even, in this case, the RDC. Now, the RDC on this scanner, which is a Philips, is not very good, and it just means that there's probably a lot of stuff being done. And this is typical from a Philips, by the way. There's a lot of stuff that is being done in the image reconstruction. And here you could see that the new data point has just been appeared. It is so there's a big difference between these two. This is why, because one of the two was actually the warming up of the signal, and so basically the SFNR is actually slightly different. You have a much better one once your scanner has been warmed up. Just to show you, you can have multiple scanner, and you directly have which one are okay or not. Here, if you're looking at another one that was a Siemens one, and you could see that in this case the general tendency of the scanner was to not go very well. At this point, they decided to do something about it, get a full hardware replacement, and then ever since the scanner has been working very well. So you can see that these kind of tools can actually be very useful for tracking over time your scanner. Anyway, that's the end of my presentation. Thank you very much.
Any quick question before we break?
Yes.
Yes. So with the advent of AI recon and denoising, how does that affect the interpretation of Weisskopf analysis and such?
Yeah, that would be a really interesting thing, because actually all of a sudden you are deviating from what is supposed to be.
Changing the rules.
You're changing the rules. So the answer is I don't know, but Nobody knows, really, and that's the big problem about AI. It's like even the manufacturers don't know what is actually happening, right? AI magic, lots of data, some black box, data looks better, we are happy. And somehow, with that, the FDA, CE marking, and etc., it was obtained by all the manufacturers for all of these tools. UKCA in the UK, same thing. But they don't know. And so for fMRI in the first place, for quantitative MRI is even worse, because you're going away from a ground truth. It's becoming very, very hard to make sure that your results are going to be comparable over time, because all of this AI reconstruction keeps being actually included. So that's, in a way, it's a right time to start something like doing a bit of quality assurance to make sure that you track. You might not know what is going to happen, but you can actually measure what's going to happen and see whether that actually affects the Weiskopf analysis, for example, or some other parameters. It will affect other parameters. It will affect the SNR, and it will probably affect the SFNR as well.
So you might recommend doing sort of a double analysis with and without the AI recon, maybe?
I mean, if you have the possibility to turn it off, yes. I can bet you with you right today that within 5 years you won't have the ability to turn it off anymore.
Of course.
So, yeah.
Thank you. So the